Good morning. Sorry, good evening. Today, we will be talking on an interesting topic continuing from our last class. It will be non-idealities in current mirror. We will see what are all the non-idealities that we take from, say, body effect or channel length modulation, okay, and how this impacts our current mirror design. We will speak about that and continue further. So welcome to lecture 15, ECE 420. So what are the things that we can look at? First, to begin with, let us understand what is refresh our memory with what is current mirror, right? And what are the non-idealities? So first current mirror is reference current, IREF. Here you will have the diode connected circuit. On the opposite side, you will have the mirror circuit where you expect the current to flow, I. So these devices are M1 and M2. VDD here, and this is your I out. What is the reference current equation? IREF is equal to half mu n Cox W over L 1 VGS1 minus VT1 whole square. What is the I out? I out current equation is half mu n Cox W over L 2 VGS2 minus VT2 the whole square. Now what will happen is, here is the ideal expressions. Now from there on comes your challenges. What are these? So if you fabricate this device in the same silicon, even if you keep them next to each other, you will not get absolutely same devices. So even if you fabricate, so what will happen? There will be some change. Some or the other change will be there. Some difference will appear. Now, these differences can be typically broadly classified into three items. One, channel length modulation, or what we have commonly been calling it as CLM. Second, you will have the threshold voltage difference. So there is going to be a VT, what we will call it as VT offset between devices, between the two transistors. And the third would be the expected matching that you want to have between devices. You will have an imperfect geometrical matching. Okay, so when these three are the devices, now you see what could be the challenge. The first challenge is CLM is called lambda. So your lambda is non-zero, and you might have, and this will impact directly your come together with your VDS. Next, VT offset. What does VT offset do? VT offset difference will be changed. So VT offset will give different ID currents. VGS will have, lambda will have different R out conditions. And imperfect geometry, you have two geometries. When you have the W, you will have the L also. So L will get impacted with CLM, channel length modulation. W will get impacted with what is the process. If there is any undercut, which will reduce the W value. So you will have a delta W coming here. So these are the three predominant factors, right? Now, with this, let us begin how channel length modulation will impact us. So how does this channel length impact? Assume all the transistors are similar. So what is the difference of the currents going to be? If you take everything common, I wrote by IF will be 1 plus lambda V ds2, correct? This will be 1 plus lambda V ds1. So these are the thing. Now what is the first assumption here? The first assumption is lambda is same for both M1 and M2. That is first assumption. Second assumption, what we do is, if we see that only an apparent difference is coming between VDS, so only VDS difference, if we see, which causes a deviation. Now, where is this deviation being caused? This deviation can be either in ideal current amplification, or you would say ideal current gain, or current mirror. So these are the two assumptions that we have while we are operating in this circuit. Now, what do we look forward with? First thing we will see is how significant is the ratio. What ratio? Find out how much this VDS ratio is going to impact the circuit. Now, how do you define what is a VDS ratio? This can be easily differentiated using small graph, where we plot the same two items here. First thing is, what is the VDS1 minus VDS2? What are the delta VDS that we see here? And then what is the ratio of the error? That is this particular error. That is 1 plus lambda VDS2 over 1 plus lambda VDS1. So this is going to be the ratio error. Now this can be defined as percentage, or it can be defined here as unit value. Now what do you observe? VDS and this ratio error is linearly dependent, right? And the only factor that is dependent on the difference is lambda. So the ratio of the graphs, or the graphs, would typically look like linear values. Right? What would be these values? These values could be lambda is equal to 0.01. This would be lambda is equal to 0.02. This could be lambda is equal to 0.03. This could be lambda is equal to 0.021. So just to show it, you could have any amount. So this is the ratio error. It could appear like this. Now, what is the impact of this change? First impact is, if your significant ratio error can appear, okay? Significant ratio error can appear even if you do not have same VDS. Without same VDS, or when the transistor do not have same VDS. Second, the ratio improves with decreasing lambda. So that is the I out by IRF ratio, or given by the ratio error. The ratio error increases with lambda decreasing. What happens when lambda decreases? Output resistance increases, 1 over lambda, right? Lambda ID. Output resistance increases. Second, now to conclude from this exercise, you can understand that for ideal or to have ideal current mirror activities, so good current mirror will have two good components. First, your VDS should be same, or VDS need to be identical. Second, you should have high output resistance. Okay, so now this is like a good problem statement, right? So how do you solve this? The way to solve this high output resistance means R out is equal to 1 over lambda ID. So how can R out be more? If lambda is less, then R out can increase. Or if ID is less, R out can increase. So these are the two methods. Okay, that is one. Now another thing what you can happen is VDS needs to be identical. How can VDS be identical? VDS can be identical if W is more, right? If W is more, your area increases, power increases, and current also increases. Okay. Now, if your another option which can happen is L needs to be small. When L is small, your delta L can be large, which will increase channel length modulation. So that is also not preferred. Correct? Come again. When you increase W, your area will increase, power will increase, and current will also increase for a given VGS. If your L decreases, that is, if you try to use short channel devices, the delta L will increase, and this will lead to channel length modulation. And channel length modulation further will lead into VDS change. So it is a circular problem. In high output impedance case, you have to reduce lambda. See, you have to reduce lambda to ensure the radio error is lesser, or you have to reduce the amount of current. Now, what is the intuition that you have? The intuition that we can use is what we have learned from previous class. What did we learn? We learned cascode structures, right? And the basic importance of cascode structure it gave was, it gave high output impedance, right? And along with high output impedance, it was able to provide isolation of nodes, right? Now we can use this trick and see how we can utilize or use the cascode structure to answer the two problems given below in the previous slide. So the first thing we will do is, let's redraw the circuit IREF. This will be VDD. In this circuit, you will now get the output device. Now, to improve the R out of this, what is the R out here? Device value. This is the R out impedance here. Now, if we know that by adding a cascode, right? By adding a cascode device with its own bias VB, this is M3. The output impedance at the drain of M3 becomes GM3 RO3 RO2. Right? Now this has improved the gain. Now what will this improve first? So here R out has increased. Along with that, what do you get? If you start plotting the voltage at these two places, this is y, x, and this is going to be p. Any three random variables you take. So what happens when you have small changes in the node P? Small changes in the node P, any perturbation here in this node does not impact this node, right? So this is the shielding property. Shielding or isolating. So you are now shielding or isolating this node Y. Okay. Now we have to use some technique such that, okay. Now next trick what you have to use, through some technique, make Vy equal to Vx. What happens? Then the effect of channel length modulation will get reduced. How do we do that? The way to do that is increase the device size. So I out is equal to I ref times W over L 2 over W over L 1. Now what happens? This now only depends upon the device geometry and device scaling. So this is the best way to do. Now just to understand, this is intuitively understanding the shielding concept. Now how do you actually do it mathematically? Mathematically, the voltage at Vx or Vy will be given as, what is the P? Any delta Vy appearing at this node is given by delta Vp times, okay, delta Vt times 1 over the Gm. That would be Gm3 plus Gmb3, right? Gm3 plus Gmb3 times Ro3. The impact of delta Vp here is reduced at delta Y using the output resistance of Gm3 over Gmb3. So this is a gain that is present here. So by this it reduces. So these are the two ways, right? We can reduce the impact of any perturbations on point P over A. So this is a nice feature. Now, but how do we generate? You can ask, how do we generate this condition such that Vy equal to Vx? Now this is a thing. How can we make Vy equal to Vx? Now, for that condition to be satisfied, you have to have a unique condition. That is this Vx voltage, right? That you see at this V gate. Now let us realize Vx equal to Vy. Now understand what is Vy condition. Vy you can get using Vb, which is your gate terminal, minus Vgs, right? Vgs is equal to Vy. Now this Vy you have to equate to Vx. So how do you reduce, how do you achieve this? That means you need to add one gate to source voltage. What is one gate to source voltage equal to? You need to add this gate to source voltage at X. So this gate to source voltage, if you have to appear it, the easiest gate to source voltage that can be added is a diode drop, right? VGS equal to VDS, right? This can be added. So you can introduce another diode drop here. So here is going to be the original M1, M2 current mirror. Now you will introduce a bias circuit stacked with VB. So this is your M3. For this circuit, now you will introduce a current diode connection. Now this diode connection will be connected to this terminal. Here will be IRF. What is this voltage value? Let us call it as N. Now, this is the two values that we have correct here. Now, what is this value now given us? This is Vx. Right? Now, what is the value at the gate terminal of the M4 device? So, what is the value if this is plus and you connect minus to ground? What is this value here? This value will be VGS of M4 plus Vx. VGS4 plus Vx. So this is the device. Now, once you have VGS4, what is the value that you need to fulfill? The value that you need to fulfill is VB minus VGS has to be equal to Vx. Now, if you connect, what will be the value of Vn that will satisfy this criterion? So VGS4 plus Vx, right? VGS4 plus Vx is the value present at Vn. If you apply Vn to this terminal, right? If you connect Vn to VB, what would be that condition if you connect Vn to VB? Then VB minus VGS will be equal to Vx. Correct? So Vn will be VGS4 plus Vx, right? This is Vn minus VGS will give you only Vx. So this will satisfy this criterion, right? Then what is the next value? Then you have to understand that this transistor and this transistor dimension should be the same. So dimension of M3 and M4 to be same or identical, right? If they are identical, then you will get VGS4 equal to VGS3. When you get VGS4 equal to VGS3, then you will be able to see the same current mirror interaction without any loss, right? So this would be the terminal that would come. Now for this to happen, what should be the condition? The dimension ratio of the mirror circuit bottom should be the same dimension ratio of the top circuit or the cascode circuit. What does that mean? So 1 and 2, W by L of, let's see here, this ratio, W by L2 over W by L1. W by L2 over W by L1 should have the same ratio as W by L3 over W by L4, right? You should note that the ratio needs to be same. The physical geometry could be different. Example, W by L2 could be 8, W by L could be 1, W by L of 1 could be 1, but W by L3 can be 2 and W by L 1 can be 1, or W by L 3 can be 4 and W by L 2 can be 2. So if you see, the ratio of 2 is maintained, but the actual geometry size is reduced. Another thing, these pair of devices 1, 2, 3, 4 need to be matched, and this would be the layout criterion. It's called matching in layout. So you would have to keep the environment same, the route same, and the via connectivity that you have needs to be the same. We will come when you understand the layouts. We will do that later. So only when this happens, you will get VGS 4 equal to VGS 3. And when you get VGS 4 equal to VGS 3, then you will get Vx equal to Vy. So this is the current mirror impact when you have. Now what will happen? Though the cascode improves accuracy, the cascode devices improve the accuracy. Now, we know that if something is improving, there must be a drawback, because analog design is all about balance. So some drawback will be there. What is that drawback? Your swing is reduced, right? Because you are having a VGS minus VT reduction. As we saw that since this is cascoded, what is the output impedance of the cascode? The output impedance also will increase by, first, when you look at the output device, so this is M3 and this is M2. Just redrawing the circuit from previous page. So here the impedance will be just R out, and the gain is GM R out. R02 is R out. Now what will happen? The gain here, the output impedance get multiplied by the gain of M3. So the R out here becomes, this is R02. The R out here becomes R02 times gain of this device, GM3 R03. So this will be the output impedance. Effective or approximate output impedance will be multiplied by this value. And this is a significant increase. So this significant increase allows you to have a very high output impedance looking into the circuit. So the R out looking into this node P will be R02 times GM3 times R03. Now this also helps in increasing the accuracy, because the error reduction will be lesser. So what does that change here? Node P, this will be node Y, this is node X, and this is node N. We will have, these are the values. Now, what is the factor that we look here? So this is the accuracy, and this is going to be the swing. So what is the swing trade-off that you will have? The swing trade-off is going to be the cascode value. How do you measure? This is your the total output here. This is VDS, right? Vx is the VGS of the previous stage. Vx. And then you will have the V over drive. What is V over drive? VGS minus VT. So your swing will reduce by 1 VGS minus VT factor, right? So this is the, in your comparison we can do is original current mirror we have the modified current mirror. How does the original current mirror look like without the second cascode stage? Here the current mirror. The VP at this node, IREF, this is I out. So what is the observation that you see here? Here, I out not equal to IREF. In fact, it will be lesser. Second, Vx not equal to Vy. This is Y, this is X. Vx not equal to Vy. And because of this, VB is chosen such that V min, VP is minimum. So these are all the problem statements. How did this get rectified? This got rectified as follows. In the modified circuit, the following modification was done. We corrected a cascode device here to the original cascode here. In this case, this value X, Y, P, N, IREF and I out. Due to addition of this device, VB is chosen such that Vx equal to Vy. Because Vx equal to Vy, VP is not minimum. And since VP is not minimum, you will get your I out equal to IREF. So this is going to be the summary. That how is your modified current mirror impacting and how this impacts your swing. And here, what happens to your swing? Your swing is given as, what is the difference here? We will mark the values here. Sorry, this plus and this minus, you will see what is the voltage drop? 1 overdrive. VGS minus VTH. Then you will have another VGS minus VTH drop. So you will have 2 drops here. Whereas in this circuit, you will only have VGS and here you will have VGS minus VTH. So this one you will have smaller swing, whereas here the circuit will have larger swing. Okay, larger swing comes because the bottom device M2, instead of having a swing of VGS minus VTH, that changes to VGS. Okay, so that is going to be the swing difference. Right, this is going to be the accuracy and voltage swing trade-off. Now, the next effect we will see is threshold, that is VT, threshold voltage effect. We'll have to change gears now. We are looking at the second effect, right? We have looked at what is this channel length modulation. Now we will look at the offset. So if you look at the threshold, what is the threshold here? Between the two devices, you have the two devices M1 and M2. Each of these devices has a VT1, VT2. Now, in case if the difference comes, what is the difference going to be? You're going to be delta VT. Where is the delta VT going to appear? The delta VT is going to appear additionally here. The difference between the two. So the delta VT is going to be VT1 minus VT2. That will appear as a difference at this VGS supply. Now, what does this mean? This means your ID, which is dependent on the difference of VGS minus VT, will get impacted. How does that? Now it will go into a ratioed effect. The ratio will be I out by I ref is equal to VGS1 minus VT1 over VGS2 minus VT2. Right? Important factor, ID is multiplied by this. It's actually dependent on the square of the voltage. So here you're going to get an impact of square of the voltage. Now, technically, sometimes we have seen very small delta VT changes do not have a much significant voltage. We do not have a number, but there is a rule of thumb. Rule of thumb is for practical circuits, up to a delta VT is equal to 10 millivolt, change is less. Change is less as the impact is less. Okay, so up to 10 millivolt can cause errors. Okay, I'm sorry. Even 10 millivolt can cause a significant change. I'll tell you I'll just show can cause a significant change. Now you look at here, delta VT. If your delta VT is equal to 10 millivolt, then the current IREF will get changed by delta VT square or 10 millivolt square. Right? This can be a big number. Right? So that is why we looked at what is the impact that we see in a ratioed circuit. So even this ratioed circuit, how does it impact? Since it is getting impacted, let us see how. Let's draw a graph where the graph x-axis is given by delta VT, and we are typically always going to be in millivolt range. We will not be much. Now what will happen in this case? In this case, you're going to have a change in the ratio. What ratio we are looking at? Your ratio of the output to the ratio of the input currents minus 1. What does that mean? I0 minus I1 divided by I1. You're going to be the current ratio error. So what does this look like? So there is a difference between ideal and imperfect current mirror. How does this look? This can be done by looking at what is the input current that is differed. So the difference in the input current can come here as, for a very large value, the current will be like this. Meaning, if your I1 is 1 microampere, your range will be bigger. But if your I1 is 100 microampere, the change will be relatively lesser, right? And typically your 10 microampere could be a decade, would be like this. So what do we observe? That there are two things we can observe, or what we'll find out. Current mirroring is good for large currents. Right? Current mirroring is good for large circuits. You see, if when your input current is 100 microampere, delta VT has a much smaller change. Right? The reason why that happens is VGS, which is directly, which depends on the current, ensures that VGS minus VT, this difference becomes small. Okay, the change in this difference becomes small, hence you will go. Otherwise, when you have low current, small current, small VGS, large current, large VGS. Right? So as you're in large VGS, if some VT goes by, the current doesn't get impacted much. But if there is a very small change in the current, a small change in delta VT also will increase the current. So here we have to be careful whenever we are doing low current biasing. Right? When you are using low current biasing in the ranges of nanoampere, you have to be careful about VT. What does this mean? You will be dependent on both on process and you will be dependent on temperature. So both process in among process voltage temperature, process also will impact, then temperature also will impact. So you have to be extremely careful while you're doing low current biasing. And this comes into picture when you're doing sub-threshold circuit operation. You will see that a lot of applications demand a sub-threshold circuit operation. In these cases where your VT is getting impacted both by process and temperature, you have to be careful about how the threshold voltage can impact your operation. Now, what else can we see? Now we have heard about process or temperature variation is we have to look at. We have only looked at what is the VT variation with respect to the current or the process till now. Now, if you look at the process and temperature impact, right? So what are the process impact? Process impact can be C-ox. How much of the C oxide is there? C oxide thickness. Depending upon oxide thickness, your C-ox will vary. Next, with the temperature, your mobility. Your temperature will impact mobility. So you have both temperature and process going to impact. Now, can we justify that? K is equal to mu n C-ox W over L, right? Now, in this particular case, let us call it as small k. Small k is equal to only mu n C-ox. Now, when you calculate this mu n C-ox, where does it get impacted with respect to the current? So the current equations change as I out by I ref is given as small k times V2, VGS minus VT2 whole square. This is K1 by VGS minus VT1. So this is a assumption that we have is here the aspect ratio is the same and the VGS is going to be the same. Now let us define a delta value for this one, delta K. So when delta K is equal to K1 minus K2 or K2 minus K1, we will see which one is applicable. We need to define K, which is given as K will be half of K1 plus K2. And then VT will be given as half of VT1 plus VT2. So this is called picking out the common mode between the two. Here you are picking the differential mode. Okay, you are looking at the differential mode. Then what happens? We get a definition for each of these terms. The terms becomes K1 becomes K, this K minus half of delta K. Okay, then K2 becomes K plus half of delta K. Similarly, VT1 becomes this VT minus half of delta VT. Then VT2 becomes VT plus half of delta VT. So we will use these ratios in our circuit analysis. So if you put back all of these values into the above equation 1, then your equation 1 becomes I out over I ref is a difference. Now K1 becomes K, K2 is here, so it is K plus 0.5 delta K, and that multiplied by VGS minus VT. VGS minus VT, this would be 0.5 VT whole square, and this would become K minus 0.5 delta K. This is VGS minus VT plus, because negative term, right? 0.5 VT the whole square. Now if you have to figure out or create dependency, right, you can differentiate these and get the value, or use a simple simplification term. Approximately this becomes, what we can do, we can take a factor out. What does this factor out mean? This K is delta K by 2, right? So this term will now become, if you divide by K, bring the K out. If you multiply and divide it by K, K plus K here, if you do that, you have 1 plus delta K divided by 2 times K. In factor, the other one is 1 minus delta K by 2K. This is these two terms. Next two terms in this VGS factor. What do we do here? We will only subtract this value. This is common, right? We'll divide this. That time K and K will get cancelled. So we will do K VGS minus VT. So these two common factors we will get cancelled out in both conditions. What will be left over with 1 minus VT by 2 times VGS minus VT whole square. Similarly below, it will be 1 plus VT divided by 2 times VGS minus VT the whole square. Now, if we assume that all these quantities are small, right? So we know that if 1 plus x or 1 minus x difference is very small, then 1 over minus x can be written as 1 plus x. Okay, so this is the approximation that we will use for this term and this term, and we will get this minus will become plus above, this plus will become minus above, and they will all there is no denominator, they will all go to the numerator. So this will be 1 plus delta k by 2k. This will become 1 plus delta k by 2k, right? Next, these two terms, 1 minus Vt by 2 Vgs minus Vt whole square multiplied by 1 minus Vt by 2 times Vgs minus Vt the whole square. So this will be the 4 terms that we get. And what do you see among these 2 terms? If you see that each of these, if you multiply with each other and you retain only the first order, only the first product, retain only first order. So what will be the first order product? 1 into 1, 1. 1 times delta k by 2k. You will have again another delta k by 2k. Finally, delta k square by 4k square. That is one term. Then internally, if you multiply all of these in that manner, finally, if you take only the terms which have got a k factor or only one Vgs minus Vt, 2 variables, you will end up with a simplification or analysis. You get I out over Iref approximately that 1 into 1 will stay back as 1, and that you will have a delta k by k, that half of it, delta k by 2k plus delta k by 2k becomes delta k by k. That you will multiply with only one VGST term. So that would be 2 Vt by Vgs minus Vt. How do you get this? If you multiply a minus b the whole square times a minus b the whole square. So what is it? A minus b times 4 times, right? So you'll only be left with 1, and the next smallest term would be the summation of these two. So Vt by 2 Vgs minus Vt times V Vgs minus Vt. So you will get 4 such quantities, right? 1 minus 2 times Vt by 2 Vgs minus Vt plus Vt divided by 4 Vgs minus Vt the whole square. So these square terms get cancelled with each other. So 2 Vt over this value, 2 Vt over this value becomes minus 4 Vt. Minus 4 Vt by 2 Vgs minus Vt. So minus 4 by 2 becomes minus 2. So you're left with this particular term. So now this would be the simplification that you would have dependency on the k and Vt. So if the percentage of Vt and k are known a priori, then we can present the worst case error we can find out. For example, if delta k by k is plus minus 5%, okay, then and delta Vt over VGS minus VT. Delta VT over 2 VGS minus VT is about plus minus 10%. Then total IREF will give you IOT over IREF ratio is given as 1 plus minus 5%, 0.05. Then plus minus 2 times 10%. So this would effectively be, instead you will put minus 2 outside, inside will be plus minus 0.1. Now this is effectively written as 1 plus minus 0.05 minus into plus minus, minus into minus plus. So this will be plus minus 0.2. Now if you take the difference, this is larger. So what is the maximum value? Plus goes with minus, so you will get 0.15. And this difference reduces, you will also get plus minus 0.15. So 1 plus minus, you take this minus sign inside, it will be 0.2, 0.05. The difference will be 0.15 along with the minus sign. So 1 plus minus 15, or this would be 1 minus plus 0.15. That means there is going to be a 15% change, or max error. Max error is going to be 15% with the tolerances that is provided. Okay, if you've got delta K and delta VT in this range, then your delta IROT by IREF will have a 15% change. So the last change that we will look at is mismatch in geometry, or it would be called mismatch in aspect ratio, or it would be called geometry. Mismatch in the geometry. So what are the mismatch that you will see? You will see a mismatch in W and you will see mismatch in L. Now, why you get these mismatches? You can see in the mask design. Okay. Second, you can go in the photolithography process. You'll have photolithography process. Last one is when you diffuse the device. So with you, all of these there. Now, if you place two such circuits next to each other, each delta W, delta L will get impacted, and this will cause a large change. And this large change is not preferred. Right? So what do we do? How to overcome this? So the way to look at it is, right? So if you have your pin tubs here, so this is going to be your W and this is going to be your L. So if there is a delta L and delta W coming here, so if you have small l minus a delta L, you will have a large difference. But if you have a large L and the same delta L, you'll have a small difference. Okay, so the way we can look at it is, increase the geometry, increase the L, increase the W to reduce the impact of delta W or delta L in your circuit. But if you do that, right, you will have delta VT offset and channel length modulation also playing a role. Okay, the change due to these two will be much lesser than the change due to delta VT. Okay, change, or you could say significance. The delta W, delta L significance will be much lesser than these two. That is why this mismatch is the third factor. But when you are looking in high current gain applications, where you want I out by Iref, to be much larger than 1. What happens in this condition? In this condition, your aspect ratio needs to be much large. What is it? Your M2 current device size has to be much large compared to M1. Now for this M1, you need to have new layout techniques. Okay. So one of the most common layout techniques that it uses, if you have your M1 sitting here, then you surround the M1 with M2. So how many M2s you have? You get about 8 M2s. So you can have a M1 is to M2, your ratio will be 1:8. And the advantage of this design technique is the proximity for each device is identical, right? And it is symmetric across 4 angles. So this is called a common centroid layout. Okay. So with this technique, what you can do is, for any ratio up to 1:8, right, you can follow this layout, but not connect the devices. For example, if you want only 1/4, right? If you only want 1/4, then you can omit the corner devices and only retain these two devices. That way, you will get 1:4. Right? It is easier to do. Now, if you want only 2, then you can connect only M2 above, 1/2 below. Retain all the 3. You will still get a 1:2 circuit. And the delta VT, delta VGS change, or your mu&C aux change will be identical. The delta will be the same. So since the delta is the same, the impact will also be consistent or predictive. Right? The aim is to have predictive loss or predictive non-linearity, such that you can control it. And this is one nice way of doing it. So this is a nice creative solution for this, right? So this way you can build one circuit, or your variation can be minimized overall. The important thing here is, in all these cases, L is fixed. Okay, only the W is multiplied with a unit W value. So if you have M1 is 1 unit, W unit device, the M2 will be integer multiple of the W unit device. So you will keep it in that way such that we can use this technique and get a reduction in the non-idealities with respect to mismatch. So whether you have a 1:4, 1:8, depending upon how you keep the layout, you can get the value, right? So these are the simple ways of doing. So in the next class, we will look at the current mirror configuration. We will look at what is the current mirror configurations that we can use and give. So what are the various methodologies that is followed?
Papa, where's my puppy?
You'll be able to hit the baseball.
Papa, where's my puppy?
She has gone down. So let us quickly summarize. Okay. First thing, in today's class, you learned what is a non-idealities, sources of non-idealities. Okay, there are three sources of non-idealities. Okay, first was VT, then W over L, then what was it? Channel length modulation, lambda. Right. Second, you saw how to use cascode to solve this problem. So the way to do is put a cascode and then put a diode structure. Put a diode structure and this structure like this. So you will introduce a cascode device here. So what this will do, you will introduce a VGS term and ensure that these two terminals, X and Y, their voltages will become Vx equal to Vy, and these two voltages, Vp and Vn, will be maintained similar to the below cascode. Right? Later we saw, or we understood that what are the impacts of the non-linearities due to Vt, due to lambda, and due to W over L, and how you can overcome all of these. Thank you. Have a great exams in this weekend.